Alright guys, we're going to go ahead and talk about your second semester final review. Alright, start with number 1. It says, in a reaction where we have 2 moles of hydrogen reacting with 1 mole of oxygen and it produces 2 moles of water, what is the ratio of hydrogen to oxygen? Okay, we know the mole ratio because we look at the coefficients. That's the number in front of the formulas. For hydrogen we see that we have a 2 in front. So there's a 2 coefficient, and then oxygen doesn't have a number, so therefore it's an understood 1. So the ratio would be a 2 to 1, or we could write it as 2 moles of hydrogen to every 1 mole of oxygen. Okay, moving on to number 2. Number 2, it says, gives us the same reaction. It says to completely convert 9 moles of hydrogen gas to water, how many moles of oxygen are required? Okay, so we see what we're dealing with. We're dealing with hydrogen, we're dealing with oxygen, so we go ahead and box those in our equation because we're going to be using those guys. And remember, every time we box something, we always write the ratio, we always write our conversion factor. We know that 2 moles of hydrogen always equals 1 mole of oxygen. Okay, and from here what we can go ahead and do is we can go ahead and work this out. Remember, we always start with what the problem gives us. We start with 9 moles of hydrogen, okay, and then we use our conversion factor, and it's just a mole to mole conversion. We go from moles to moles, so therefore we're just going to be using this conversion factor, and since we have moles of H2 on top, we put 2 moles of H2 on the bottom, and then we put our 1 mole of O2 on the top, multiply the top, divide by the bottom, and we get an answer of 4.5, and that would be moles of O2. Alright guys, moving on to number 3, and it says for the reaction where we have sodium nitrate, it decomposes into sodium nitrite and oxygen. It says how many moles of sodium nitrate are produced from the decomposition of 100 grams of sodium nitrate. Okay, so these are the 2 things we're dealing with. So anytime we're dealing with that, we always box what we're dealing with. Here is our nitrate, and then here is our nitrite. Okay, and we go ahead and write down the mole ratio form because we always use the mole ratio. So 2 moles of sodium nitrate equals 2 moles of sodium nitrite. Okay, next thing we see is that we have 100 grams of sodium nitrate. So whenever we do, we see grams of anything, we have to use the molar mass of sodium nitrate. Okay, so we get to review molar mass. Remember, we take what we have. Sodium nitrate has sodium, nitrogen, and oxygen. We have 1 sodium, we have 1 nitrogen, we have 3 oxygens. We multiply them by their mass on the periodic table, and 16.00. Multiply them out, add them all up, and we should get a mass of right around 85 grams. So we know that 85 grams of sodium nitrate equals 1 mole of sodium nitrate. Okay, so we can go ahead and we can set this problem up. Always start with what the problem gives us. It gives us 100 grams of sodium nitrate, which is NaNO3. Okay, and we set it up. And since we have grams of NaNO3, we need that on the bottom, so we're going to put 85 grams of NaNO3 on the bottom, which equals 1 mole of NaNO3. Okay, we use that conversion factor, it's done. Okay, we have moles of NaNO3, so we need to put that on the bottom, and that would be 2 moles of NaNO3 equals 2 moles of sodium nitrite. And then all we do is we go ahead and we multiply the top, multiply the bottom, and we see that we will get right around 1.1765 moles of sodium. That should be sodium nitrite. Okay guys, moving on to number 4. It says for the reaction, we're using the same reaction as in 3. It says calculate the percent yield if 500 grams of sodium nitrite reacts with excess oxygen to produce 575 grams of sodium nitrate. Okay, and it wants to know the percent yield. Remember that percent yield is actual divided by theoretical times 100. So the 575 grams of nitrate is going to be our actual, so we need to find our theoretical. So what we're going to do is we're going to do a gram to gram conversion from sodium nitrite to sodium nitrate. So we start off, and if we're doing a gram to gram conversion, we need the molar masses of each of them. So we calculate those. Remember, we just add up everything that's in the equation, and we know that 1 mole of sodium nitrite is going to equal right around 69 grams of, sorry, that's nitrite, sodium nitrite. And then we know that 1 mole of sodium nitrate equals right around 85 grams of sodium nitrate. Okay, and we're dealing with nitrate and nitrite, so we also need the mole ratio. We know that 2 moles of nitrate equals 2 moles of nitrite. Okay, so we go ahead and we start with our 500 grams to kind of start us off. And we take that with our 500 grams, and that is of nitrite, which is NaNO2. And if grams is on top, grams has to go on bottom, so we put 69 grams of NaNO2 equals 1 mole of NaNO2. We're done with that conversion factor, can't use it again. So now the only other thing that says moles of NaNO2 is our mole ratio. So 2 moles NaNO2 equals 2 moles of NaNO3. Okay, can't use that conversion factor again, we keep going. And we see the only thing that we have left, we put 1 mole of NaNO3 on the bottom, which equals 85 grams of NaNO3. We go ahead and we work that out, multiply the top, multiply the bottom, divide everything out, and we get 615.9 grams, and that is going to be our theoretical. So we plug in our 575, all divided by 615.9 times 100, and we get a percent yield, and our answer should be right around 93.5%. Alright guys, moving on to number 5, it says explain the kinetic molecular theory and how it relates to solid, liquids, and gases. Guys, remember the kinetic molecular theory explains how solids, liquids, and gases behave, and we're looking at a molecular level, and basically we're looking at how much they move. Remember that solids move the least, they kind of vibrate in place. Liquids move a little bit more than solids. They have the ability to flow, and that's why we call them fluids. And then gases, they're not connected at all to each other. They're moving around as fast as possible with no intermolecular forces. Now, in number 6, it says, when do ideal gases resemble real gases? Remember, ideal means perfect. Real gases are what we actually have in the real world. And real gases, they look like ideal at very, very low pressures and very, very high temperatures. Okay, moving on to number 7, it says convert the pressure. We have 3.5 atmospheres to kilopascals. we need to know our conversion factor. Remember, 1 atmosphere equals 760 torr, which is 760 millimeters of mercury, which equals 101.325 kilopascals. Got to know that for our test. So here we're dealing with atmospheres. We know that 1 atmosphere is going to equal 101.325 kilopascals. Okay, that's our conversion factor. Remember, we always start with what the problem gives us. It gives us 3.5 atmospheres. We set it up. Atmospheres go on the bottom, so we put 1 atmosphere on the bottom. Got that from right there. We put our 101.325 kilopascals on the top. See the units cancel, and we go ahead and we multiply it out, and we should get an answer right around 354.55 kilopascals. Alright guys, moving on to number 8. It says the pressure of a sample of hydrogen is 4 atmospheres in a 400 milliliter container if the container is compressed to 10 milliliters without changing the temperature. So temperature is constant, we don't worry about that. What is the new pressure? So here we're dealing with the Boole's law problem. So our equation is going to be P1 V1 equals P2 V2, because remember, temperature is held constant, so we don't need it. Okay, go ahead and label everything we have. So our P1 is going to be 4 atmospheres, our V1 is going to be 400 milliliters, and then our V2 is going to be 10 milliliters. So we set everything up where we have our 4 times 400, okay, which equals our P2, which we're looking for that, and our V2, which is 10 milliliters. Okay, so we go ahead. How do we get P2 by itself? We divide by the 10 milliliters. So what we'll have is P2 equaling 4.0 times 400, all divided by 10, and we should get an answer right around 160. And that would be our unit in pressure, which would be atmospheres. Okay, moving on to number 9. Here we see that says at 8 degrees Celsius the volume of a gas is 50 milliliters. At the same pressure its volume is 75 milliliters. What is the temperature? So we are dealing with a V1 all over T1 equals V2 over T2, which we know that this is a Charles law problem. So we label everything that we have. We see that this is our T1, here is our V1, and then we have a V2. So we are going to be solving for our T2. So we go ahead and set it up. So we put our 50 milliliters on top, and then our 8 degrees Celsius, which remember we always change it to Kelvin, which we always add 273, which that one's going to come out to be 281 for our Kelvin temperature. It equals our V2, which is going to be 75, and we're searching for our T2. Guys, remember here when we're doing this, cross multiply and then divide. So we're going to have our 281 Kelvin times 75, all divided by 50 milliliters, and we should get an answer of 421.5 Kelvin for our temperature. And then moving on to number 10, it says as the temperature of a sample of gas falls from 35 degrees Celsius to 20 degrees Celsius, its pressure falls to 250 millimeters of mercury. If the volume didn't change, what was the original pressure? So here we are dealing with the Gay-Lussac's problem. So we have a P1 all over T1 equals P2 all over T2. Okay, go ahead and label everything. Our original temperature is going to be T1, which is right here. Here's our T2, and this is going to be our P2. Set everything up, And remember, change our temperatures into Kelvin. And what we're going to have is we'll have our P1, which is what we're searching for, all over our temperature of 308, which that equals our our pressure, which is 250 millimeters of mercury, plus our 20 degrees Celsius, which is 293 Kelvin. Okay, guys, right here, remember, cross multiply. So we take our 250 times our 308 and all divided by 293, and we should get an answer right around 262 point, we'll round it to 0.8, and that would be our new pressure. So that'd be in millimeters of mercury. Alright guys, moving on to number 11. It says, what is the pressure exerted by, it gives us 2 moles of a gas with a temperature of 20 degrees Celsius at a volume of 9.5 liters. So it's searching for pressure. We're going to be using the equation Pivnert, PV equals nRT. Okay, labeling everything out, we see that this is going to be our N for moles. This is going to be our temperature. Remember that it has to be in Kelvin, so we go ahead and add 273 to it, and we'll get 293. And then it has to be in liters. Remember that you have to have liters, atmospheres, moles, and Kelvin. So our pressure is going to be in atmospheres. Remember that R is always going to be 0.0821 when we set it up. So we go ahead and write everything down, set it up. We're searching for pressure. Okay, so to get pressure by itself, we always divide by our volume. So we have P equals our moles of 2.1, our R, which is always the same, 0.821, all times our temperature of 293 Kelvin, and then we divide that by our 9.5 liters, and we should get a pressure in atmospheres of 6.33 ATMs. Alright guys, moving on to number 12, it says distinguish between the compressibility of liquids, gases, and solids. Remember that solids are non-compressible, liquids are semi-compressible, meaning they can be compressed a little bit more than solid cans, and gases are very compressible. We can compress them the most. Okay, moving on, it says define intermolecular forces. Intermolecular forces are the forces of attraction between molecules that are strongest in the solids. Remember, it's just the force that holds everything together. Okay, it's the force in between each molecule. Types of those, we talked about hydrogen bonding, dipole, and London dispersion forces. Okay, define vaporization. Vaporization is turning from a liquid into a gas. And then moving on to 15, what is the difference between a crystalline solid and an amorphous solid? A crystalline solid, remember, it has a regular repeating pattern. It's geometrically symmetrical, nice, organized pattern. An amorphous solid is an irregular pattern. It's very disordered and does not follow that nice geometry. It's just very irregular. Okay guys, moving on to number 16, it says define triple point. The triple point is the point at which all 3 phases can exist, meaning we have the solid, liquid, and gaseous phase all together. Now 17, it says the phase diagrams are used to show what? These are the diagrams that are used to show the temperature and pressure at which substances changes phases, meaning the temperature and pressure at which we go from a solid to a liquid to a gas, and how pressure relates to temperature, and if we change the pressure, what happens to the boiling point, melting point, things like that. Number 18, it says define the critical temperature. The critical temperature is the temperature at which a gas can no longer be compressed at any pressure back to a liquid. So it's the temperature at which we can no longer have the liquid phase. We can only have the gaseous phase no matter what the pressure is. Alright guys, moving on to number 19, it says which of these substances is the most volatile and least volatile shown in the figure. When we're looking at volatility, guys, it's the one that's going to boil the quickest, meaning at the lowest temperature. So if we're looking at these pressure temperature readings, we see that most volatile is always going to be benzene, and we see that the least volatile is always going to be the one that boils last or boils at the highest temperature. So we see that the least volatile is going to be the alum. Alright guys, moving on to number 20, it says define homogeneous mixture. Give an example. They are uniformly mixed and one cannot make a distinction between the parts, meaning example of those would be like salt water, sugar water, things like that. You can't look and see the parts inside of it. Moving on to 21, it says define electrolytes and give some examples. Electrolyte is an aqueous solution that conducts electricity. These are any ionic solutions, anything that ionizes and creates a positive and negative charge. Also acids are going to be electrolytes. We see number 22, it says define non-electrolytes. A non-electrolyte is an aqueous solution that does not conduct electricity. When we're looking at those would be covalent type compounds. And then finally finishing with 23, the factors that influence the rate of dissolution. So we see that those are concentration, surface area, agitation, and temperature. Okay? Concentration, surface area, agitation, and temperature.